Hello everyone, a very good morning. Thank you for the kind introduction. I hope you guys are doing well in this pandemic time. I am Nirmay Madhok, a third year PhD student at Sparkler Purdue University, USA. It's a great pleasure for me to be able to present our work on resonant electroquasi-static human whole body powering and communication SoC with automatic maximum resonant power tracking. In application like physiological signal monitoring and secure authentication, low data rate but extremely low power secure communication is required around the human body. In the recent years, human body communication has emerged as a power efficient alternative to traditional wireless communication such as Bluetooth and Zigbee. Even though today's human body communication transceiver offer low loss and low power consumption, there is a strong need of making the entire operation batteryless and perpetual. To the end of this presentation, I will discuss the first implementation of simultaneous power transfer and efficient communication through the human body using specific resonant modes that facilitate both the power and data transfer. I will also discuss a real-time maximum resonant power tracking or MRPT circuit which ensures increased efficiency, eliminating the dependency of signal transfer on different body postures, movement and other physical variables such as device size and transmitter to receiver distance. I will begin the presentation with the need of human body powering and efficient communication along with the limitation it encountered during the system level implementation. I will also discuss the theoretical concept of the implemented work to overcome the limitation during power and data transfer. In the follow-up section, the discussion will be on the circuit level implementation and measurement results. Finally, I will compare this work with state of the art and conclude. First, let's discuss the motivation of this work. Low power secure communication is one of the key features of human body communication. Conventional wireless body area networks, such as Bluetooth, suffer from high power requirement and physical signal leakage, whereas EQS HBC utilizes the conductivity of the human body to use it as a communication medium and keeps the signal confined within a close proximity of the body. This makes the communication protected and not easily snoopable to the external hacker. Although countless works have been done to show the communication and powering between the wearable devices using HBC, but the whole body power transfer in variable scenario is not demonstrated yet. Along with that, if we consider a real device to device interaction in variable scenario, the communication power bumps up significantly due to inclusion of the plate to plate device capacitance in the system. This plate to plate capacitance CP act as an additional load to the transmitting device and consumes a lot more power, reducing the efficiency of the system. In this work, we have proposed a simultaneous data and whole body power transfer method along with the resonance cancellation technique to eliminate the effect of parallel plate to plate capacitance. The key contribution of this work is to minimize the power consumption during data communication, maintaining the ultra low power nature of HBC and the same time maximizing the peak power transfer during whole body power transfer. Before I move forward, allow me to discuss the theoretical concept behind the implemented work. On the right side of the screen, two capacitively connected devices are shown. The E field line associated to the floating electrode of the transmitter and receiver to the earth ground generates the return path capacitance C return TX and C return RX. Similarly, the field line between the body and the earth ground generates body capacitance C body. The load capacitance CL can be realized by the field line between the parallel plates of the receiver. A resistive element RRX parallel to CL can be realized for any amount of resistive power transfer to the receiver. Combining all this lumped element along with the transmitter and a source resistance RS, we can have the biophysical model of EQS HBC. All the previous state of the art explained the voltage mode communication of HBC based on this model and got ultra low power operation. But when we started working with real devices, a new capacitance comes into the picture, which is the plate to plate capacitance CP at the transmitter side, realized by the field line between those transmitter electrodes. While working with variable, CP should be included in the model, and this capacitance plays a major role in defining the overall power rating of the system. Consideration of CP makes the model more realistic for variable, at the same time giving the true indication of power rating for data and power transfer. Now, let's see how CP changes the characteristic of the overall communication. In this model, if we consider ZC is the equivalent impedance to the right side of RS, the overall load seen by the transmitter become RS plus ZC. At EQS frequency range, ZC is much higher compared to the source resistance RS. So we can neglect RS and can assume the entire transmitted voltage is coming across ZC. So if we try to find the power consumption at the transmitter side, which can be given by this expression. Now, in ZC, CP comes parallel to the series combination of C body and C return TX. C body has a value of 100 to 200 picofarad and C return is in 1 picofarad range. So, if we consider the series combination of C body and C return TX, the effective capacitance comes in 1 picofarad range. This 1 picofarad effective capacitance, along with 30 picofarad CP, gives overall capacitance dominated by CP. Hence, at the transmitter side, the power consumption is mostly due to the device capacitance CP. Now that we have understood the biophysical model, let's see how we can optimize it for efficient power transfer. If we neglect the loading effect, the transmitted voltage first gets divided between C body and C return TX. The voltage available across C body further gets divided between CL and C return RX. The voltage division between C body and C return TX can be represented by this factor, whereas the voltage division between CL and C return RX can be represented by this factor. And the expression inside the third bracket gives the indication of maximum open circuit voltage available at the receiver side. Now, if we consider the half power point, the maximum peak power can be represented by this expression with RRX as a resistive load in matched condition. From the expression, we can see that the maximum peak power transfer can be increased by controlling the capacitances and VTX. Out of these capacitances, we don't have control over return path capacitances and body capacitance, because these capacitances are with respect to the earth ground. So to increase the maximum peak power, the available option we have maximizing VTX and minimizing the load capacitance CL. We maximized VTX by series resonance at the transmitter side and cancels the load capacitance CL by parallel resonance at receiver side. Series resonance increases the transmitted voltage by a factor Q, at the same time reduces the effective impedance seen by the transmitter. So low impedance or boosted voltage helps to inject more power into the body. At the receiver side, cancellation of CL by parallel resonance helps to increase the received potential by a factor Q. The combination increases the overall maximum peak power transfer by a factor of Q to the power 4. Now we have found the condition for efficient power transfer between the variables. Let's see the condition for efficient communication. In voltage mode communication, we want to maximize the effective received voltage for a given transmitted power. So in a voltage mode communication, FOM should be maximizing the received voltage with minimum power consumption at transmitter side. Now, if we see the expression for FOM, it can be maximized by increasing ZC and by decreasing CL. Here, we can't reduce VTX because the driver circuit of the transmitter will have certain minimum voltage requirement, and we are already operating at minimum possible voltage to make the communication ultra low power. Now, ZC can be increased by inserting a parallel inductor at the transmitter side, and a load capacitance CL can be cancelled out by another parallel inductor at the receiver side, as done during power transfer. Parallel resonance at the transmitter side does not change the transmitted voltage but decreases the transmitted current by a factor of Q, which reduces the power consumption at the transmitter side by a factor Q square. At the receiver side, cancellation of CL by parallel resonance helps to increase the received voltage by a factor of Q. The overall combination increases the FOM of the voltage mode communication by a factor Q to the power 3. This is the summarization of the theory we discussed. We can see for power transfer, series resonance is better, and for voltage mode communication, parallel resonance is better. We also see in parallel resonance, a weak driver can be used for voltage mode communication, as the current delivered by the transmitter during parallel resonance is very small compared to the current in power transmission during series resonance. Till now, we have discussed the resonance frequency for the communication and powering. Let's talk about the dependency of the resonance frequency on the external parameters. Plate-to-plate capacitance Cp and return path capacitance C return mostly determine the resonance frequency. Cp increases with device size and C return increases with the size of the floating electrode. C return also changes depending on the body posture and ground distance. Therefore, tracking of the resonance frequency for increased efficiency is extremely important. To track the resonance frequency, we used an automatic frequency sweep with small frequency increment. After the detection of the resonance frequency, it is locked at that frequency value and the power or data transmission is done. This is the proposed block level architecture of the Resonant EQS HBC trans receiver system. A battery operated hub unit operates in 3 different phases, interact with a batteryless node unit, operates in sync with the hub for power reception, and data transmission. Hub utilizes series resonance with a powerful driver during power transmission, whereas the node receives the power and store it for future use through an energy harvester circuit. During the communication, both use parallel resonance, which reduces the power consumption significantly. Let's discuss the circuit level implementation. This is the proposed RHBC hub architecture, which has six major components. An on-chip clock generator. The clock generator is a ring oscillator designed using starred inverter, which can also be digitally controlled. A duty cycle corrector block generates clean clock for better operation. Using a 6-bit digital code, the frequency can be varied from few hundreds of kilohertz to few megahertz. Next component is a synthesizable TX unit. Based on the mode selected, either it sends signal to the communication port or to the powering port. It also has a PRBS generator and can take external data for transmission. The communication port of the hub operates in parallel resonance. The driver for the communication is implemented using 4-stage inverter, which is capable of driving maximum 30 picofarad load during communication. The next component of the hub is a powering port which operates in series resonance. It is designed using 6-stage inverter to ensure low source resistance and high current during power transfer. The next part is a feedback loop. It is one of the most crucial part of the hub unit as it tracks and logs the transmission frequency at resonance. The signal exerted to the body during the frequency scan phase is initially sampled by a capacitive divider network and fed back to the chip. The sensed signal first passes through a peak detector. The peak detector is basically a passive envelope detector which stores and compares the consecutive envelope information. During the scanning phase, as frequency changes, the amplitude increases and becomes maximum at resonance, and after that, the amplitude starts to fall. If we compare the amplitude of two consecutive scan frequencies, initially we will be receiving all 1 and then after the resonance peak, all zeros. The transition of 1 to zeros signifies the position of resonance peak. The control unit receives the resonance peak information from the peak detector and logs the resonance frequency at the end of the scan phase. After that, it initiates the data or power transmission phase depending on the mode selected. The last component of the hub unit is the RX frontend, which uses communication port to receive data. It utilized an ultra-low power design of RF amplifier, envelope detector, baseband amplifier, sampler, and oversampling CDR. This is the batteryless RHBC node architecture. Like the hub architecture, node architecture can be divided in 4 major components. An energy harvester to receive power sent from the hub. The energy harvester has a n-stage voltage rectifier, reference generator followed by a voltage regulator. Highly duty cycled operation enables sufficient energy storage and power generation for communication. An on-chip clock generator, like what we described in the hub unit, generates the clock for proper node operation. The RX frontend and the TX node unit are the same design used in the hub and use parallel resonance for data transfer. Now we have an overall understanding of the Resonant EQS HBC transceiver system design. Let's investigate some of the measurement results. This is the die micrograph of the proposed transceiver. The proposed design is fabricated in TSMC 65 nanometer low power technology and has an area of 0.17 square millimeter. First, look into the transmitted voltage and power during the series resonance. We can see the transmitted voltage and power get boosted by a factor Q and Q square respectively at resonance frequency because of the series resonance action. Higher supply voltage helps to deliver more power to the body and increases quadratically with supply voltage. This is the plot of transfer power and transfer efficiency for different supply voltages. The first plot shows the power transfer characteristic during a machine-to-machine power transfer with 37% efficiency, whereas the second plot shows the characteristic during variable tabletop scenario with 3% efficiency. The peak power is 240 microwatt for the first case and 28 microwatt in the second case. This is the overview of the power transfer during different HBC scenarios. As return path cap decreases from left to right, the transfer power number also decreases in the same manner. As we can see in the true variable scenario, due to the resonance cancellation, we can have increased power delivered with efficiency up to 7%. This is the measurement result of the receiver unit present in the hub and node architecture. The first graph shows the bottom curve for 20 kbps data rate with 0.56 UI opening at 10 to the power minus 5 BER. The second curve shows the input power versus BER for different data rates. The third curve shows the reduction of the data transmission power when parallel resonance is used to cancel out the plate-to-plate capacitance CP. The proposed design reduces 33% data communication power by adapting parallel resonance compared to the non-resonant EQS scenario. This is the time domain waveform during the power transfer. The initial 2 milliseconds is used for scanning and to detect the resonance frequency. We can see the frequency of the oscillator changes from 100 kHz to few MHz in steps. At the end of the scanning phase, the frequency is locked at the resonance and the transmission phase begins. This is the real-time demonstration of the maximum resonant power tracking or MRPT for the proposed architecture. Initially, it is going through the frequency scanning phase, and at the end of it, the frequency is locked to the resonance for transmission. Let's compare the work with state of the art. Evolution of variables can be divided in two different categories, for communication and for powering. When we consider the state of the art for variable communication between two devices with a plate-to-plate capacitor of 30 picofarad range, the communication power goes up to few tens of microwatt. On the other hand, if we consider the state of the art for variable powering, almost all of the previous works are not capable of delivering power to the whole body. In ISFC 2020, an inductive method was demonstrated for human body powering for tabletop devices with 1 microwatt worst case power transfer at 0.3% efficiency. But the tabletop scenario makes the method improper for true HBC implementation. In this work, we have utilized the resonant EQS to demonstrate the first simultaneous body communication and whole body powering through human body on the same SoC. Our proposed design achieves 37% efficiency for machine to machine, 3% efficiency for a tabletop device, and 7% efficiency for a variable-variable interaction scenario, which are all independent of channel length, that is, whole body powering. The current design utilizes the body channel for the first time to enable simultaneous data communication at 2.19 microwatt power budget, along with whole body power transfer, making batteryless perpetual body nodes a reality. This is an 100x improvement in body coupled power transfer efficiency and greater than 10x improvement in peak power transfer for longer channel length compared to the previous year work. This is the comparison table for power transfer with state of the art. As we discussed earlier, our proposed work can transfer 5 microwatt variable power in whole body with 7% efficiency. This is greater than 100x improvement in body coupled power transfer efficiency and greater than 10x improvement in peak power transfer for longer channel HBC interaction. This is the comparison table for data communication, which shows the current design enables data communication at 2.19 microwatt power budget even with 30 picofarad load. The receiver can operate at 72 nanowatt power budget, including an on-chip clock generator and oversampling CDR. Now I will conclude the presentation. So in the summary, this paper represents the first thorough theoretical development of resonant EQS HBC biophysical model, transfer function equations, and FOM for communication. While we have shown Q to the power 4 benefit during power transfer due to the series resonance and Q to the power 3 benefit during voltage mode communication due to the parallel resonance. We have also proposed the first microwatt solution for channel independent variable whole body power transfer with maximum power point tracking at EQS frequency region. Resonance cancellation has been shown to demonstrate the first 2.19 microwatt data communication transmitter while driving 30 picofarad plate-to-plate device capacitance. The design also includes an all-chip digitally controlled clock generator for frequency variability and energy harvested powering in the HBC node for batteryless perpetual operation. I would like to thank you for the kind attention and would be happy to answer your questions. Thank you.